Good morning, students. Today, modulus or absolute value of complex number. First, if suppose the complex number z equals to x plus iy, the complex number z equals to x plus iy. Now, the modulus of z, it also mod of z, or it is also denoted in parallel lines mod z, that equals to square root of real part square plus imaginary part square. Mod z equals to square root of real part square plus imaginary part square. The real part is x, imaginary part y. It is also called absolute value of the complex number z, modulus or absolute value of z. Now, here z bar equals to x minus iy, the conjugate of z. Z bar equals to x minus iy. Now, here mod of z bar equals to also square root of x square plus here imaginary part minus y whole square, or that equals to square root of x square plus y square. Next to minus z equals to z equals to x plus iy, then minus z equals to minus x minus iy, or that equals to mod of minus z equals to square root of, here real part is minus x, imaginary part minus y. Now, minus x whole square plus minus y whole square, that equals to square root of x square plus y square, square root of x square plus y square. Similarly, minus of z bar equals to minus of x minus iy, that equals to minus x plus iy, for implies mod of minus z bar equals to square root of minus x whole square plus y square, that equals to square root of x square plus y square. Means, therefore, mod z equals to same as mod of z bar equals to mod of minus z equals to mod of minus z bar. These four are equal. Mod z equals to mod z bar equals to minus of mod z equals to minus of mod z bar. The four are equal. All are same in magnitude. Next, if suppose z is a complex number, let z equals to x plus iy, for implies its conjugate complex number z bar equals to x minus iy, x minus iy. Now, z into z bar equals to x plus iy into x minus iy, a plus b into a minus b, that equals to x square minus iy whole square, that equals to x square minus I square y square. But I square equals to minus 1, that equals to x square plus y square, x square plus y square. Now, therefore, z bar equals to mod z whole square, or it is same as equals to mod of z bar whole square, or it is same as minus of mod z whole square, or equals to minus of mod z bar whole square. All are same. Very important this condition. Now, z bar equals to mod z square or mod z bar square, or minus z whole square or minus z bar whole square. Next, now mod of Z1 Z2 equals to mod Z1 into mod Z2. If Z1 Z2 Z1 comma Z2 are two complex numbers, then mod of Z1 Z2 equals to mod Z1 into mod Z2. Now solution: mod of Z1 Z2 whole square, mod of Z1 Z2 whole square. Now you know from previous condition, mod Z whole square equals to Z into Z bar, Z into Z bar. Now here at place of Z equals to consider Z1 and Z2. Now it is equals to Z into means Z1 Z2 into Z1 Z2 bar, Z1 Z2 bar. Now that equals to Z1 Z2 into Z1 bar into Z2 bar. That equals to here Z1 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 bar into Z2 Z2 bar. But Z1 into Z2 bar equals to, or Z into Z bar equals to mod Z whole square. Similarly, Z1 into Z bar equals to mod Z1 square into similarly second mod Z2 square. It is for mod of Z1 Z2 whole square. Therefore, mod of Z1 Z2 equals to mod of Z1 Z2 equals to mod Z1 into mod Z2, mod Z1 into mod Z2. It is also very important in solving the problems in complex numbers. Next, if Z1 comma Z2 are two complex numbers, then mod of Z1 by Z2 equals to mod Z1 by mod Z2, mod Z1 by mod Z2. Now see it, solution or proof. Now mod of Z1 by Z2, it also can be written as mod of Z1 into 1 by Z2. Now in previous condition, mod of Z1 into Z2 equals to mod Z1 into mod Z2. Similarly, here it is equals to mod Z1 into mod of 1 by Z2. That equals to mod Z1 by mod Z2. Therefore, mod of Z1 by Z2 equals to mod Z1 by mod Z2. It is also very important formula solving the problems in complex numbers. Next, if Z1 comma Z2 are two complex numbers, then mod of Z1 plus Z2 whole square equals to mod Z1 square plus mod Z2 square plus 2 into real part of Z1 into Z2 bar, Z1 into Z2 bar. Now proof. Take left hand side LHS mod of Z1 plus Z2 whole square, mod of Z1 plus Z2 whole square equals to, now you know from previous conditions, mod Z square equals to mod Z, just see, if Z1, Z2 are two complex numbers, then mod of Z1 plus Z2 whole square equals to mod Z1 square plus mod Z2 square plus 2 into real part of Z1 into Z2 bar. Now solution or proof. Take left hand side mod of Z1 plus Z2 whole square equals to, first mod Z whole square equals to Z into Z bar, Z into Z bar. From previous conditions, mod Z equals to Z into Z bar. Now here Z1 plus Z2 consider one complex number, then its whole square equals to Z1 plus Z2 into Z1 plus Z2 bar, Z1 plus Z2 bar. Now that equals to Z1 plus Z2 into Z1 plus Z2 whole bar equals to Z1 bar plus Z2 bar, Z1 bar plus Z2 bar. Now multiply these two factors, Z1 into Z1 bar plus Z1 Z2 bar plus Z2 Z1 bar plus Z2 Z2 bar. But here Z1 into Z1 bar, that equals to mod Z1 square, mod Z1 square. Next to the last term, Z2 into Z2 bar equals to Z2 bar, mod of Z2 whole square plus Z1 Z2 bar plus Z2 Z1 bar, that equals to mod Z1 square plus mod Z2 square plus Z1 Z2 bar plus, now this term can be written as Z1 Z2 bar whole bar Z2, Z1 whole bar equals to Z1 bar Z2. It can be written as Z1 Z2 bar whole bar. Now see it. If suppose Z equals to X plus Iy, Z bar equals to X minus Iy, Z plus Z bar equals to Z plus Z bar. Add these two, we get 2x plus Iy minus Iy get cancelled. That equals to 2 into, here x nothing but real part of Z, real part of Z, means always Z plus Z bar equals to, Z plus Z bar equals to 2 into real part of Z, 2 into real part of Z. Now that equals to, here Z1 mod Z1 square plus mod Z2 square plus this value equals to, if suppose consider it is one complex number, now second one is its conjugate, now that equals to 2 into, from this condition, 2 into real part of Z1 Z2 bar. Now therefore mod of Z1 plus Z2 whole square equals to mod Z1 square plus mod Z2 square plus 2 into real part of Z1 Z2 bar. Next, if Z1 comma Z2 are two complex numbers, then Z1 minus Z2 mod square equals to mod Z1 square plus mod Z2 square minus 2 into real part of Z1 Z2 bar. Z1 Z2 bar. Now here mod of Z1 minus Z2 whole square. Mod of Z1 minus Z2 whole square. Now you know from previous conditions mod Z square equals to Z into Z bar. Z into Z bar. Now here Z1 minus Z2, it is also a complex number. Now it can be written as Z1 minus Z2 into Z1 minus Z2 bar, because mod Z square equals to Z into Z bar. Now that equals to Z1 minus Z2 into Z1 bar minus Z2 bar. That equals to Z1 into Z1 bar minus Z1 into Z2 bar minus Z2 into Z1 bar minus of minus plus Z2 into Z2 bar. But Z into Z bar equals to mod Z square, means mod Z1 square. Similarly, last term Z2 into Z2 bar equals to mod Z2 whole square. In these two terms minus take common, Z1 Z2 bar plus Z2 Z1 bar. That equals to mod Z1 whole square plus mod Z2 whole square minus Z1 Z2 bar plus the second term, this can be written as Z1 Z2 bar whole bar. That equals to mod Z1 square plus mod Z2 square minus Z1 Z2 bar plus Z1 Z2 bar whole bar. It can be written as 2 into real part of Z1 Z2 bar. Z1 Z2 bar. Therefore, mod of Z1 minus Z2 whole square equals to mod Z1 square plus mod Z2 square minus 2 into real part of Z1 Z2 bar. Z1 Z2 bar. Next. Now, in these two conditions, here mod of Z1 plus Z2 whole square equals to mod Z1 square plus mod Z2 square plus 2 into real part of Z1 Z2 bar. Next, mod of Z1 minus Z2 whole square equals to mod Z1 square plus mod Z2 square minus 2 real part of Z1 Z2 bar. It is first result, next it is considered second. If suppose adding both 1 plus 2 equals to, how much you get? Mod of Z1 plus Z2 whole square plus mod of Z1 minus Z2 whole square. That equals to, here this term get cancelled by adding these two, mod Z1 square plus mod Z1 square, 2 mod Z1 square plus mod Z2 square plus mod Z2 square, 2 mod Z2 whole square. Now that equals to 2 into mod of Z1 square plus mod of Z2 square. Therefore, Z1 plus Z2 whole square plus mod of Z1 minus Z2 whole square equals to mod of Z1 plus Z2 whole square plus mod of Z1 minus Z2 whole square equals to 2 into mod Z1 square plus mod Z2 square. Similarly, from second equation subtract first one, we get, first equation minus 1 minus 2 equals to mod of Z1 plus Z2 whole square minus mod of Z1 minus Z2 whole square. That equals to, subtract from first equation to second equation, mod Z1 square cancel, mod Z2 square cancel. Here minus of minus place 4 of real part of Z1 Z2 bar, mod of Z1 plus Z2 whole square minus mod of Z1 minus Z2 whole square equals to 4 into real part of Z1 Z2 bar. Next to if suppose Z is a complex number, Z equals to, consider x plus I by, Z equals to x plus I by. Now for implies mod Z equals to, square root of x square plus y square, square root of x square plus y square. Now always if suppose Z equals to x plus I by, now mod of real part of Z, what is mod of real part of Z equals to x mod, and mod of imaginary part of Z equals to mod y, mod y. Now always mod of real part of Z, mod of real part of Z equals to, it always equals to mod x, or it also can be written as root of x square. Now root of x square equals, always it is a positive quantity, that's why mod x, it is less than or equals to square root of x square plus y square, square root of x square plus y square. If suppose imaginary part of some value, any value x square plus root of x square plus some value, it is more than x square. If suppose y equals to 0, imaginary part is 0, we get root of x square equals to x square. Now therefore from this inequality, mod of real part of Z is less than or equals to, it is nothing but mod Z, root of square root of x square plus y square equals to mod Z. Next, similarly, what is imaginary mod of imaginary part of Z equals to mod y, or it also can be written as root of y square. it is less than or equals to square root of x square plus y square, because only x equals to 0, both are equal, otherwise root y square must be less than square root of x square plus y square. Now therefore imaginary part, mod of imaginary part of z less than or equals to mod z, equals to mod z. Next, if z1 and z2 are two complex numbers, then mod of z1 plus z2, it is less than or equals to mod z1 plus mod z2, mod z1 plus mod z2. Now see it. First solution, mod of z1 plus z2 whole square equals to, now you know mod z1 square plus mod z2 square plus 2 into real part of z1 z2 bar, z1 z2 bar. In previous result, mod of z1 plus z2 whole square equals to mod z1 square plus mod z2 square plus 2 into real part of z1 z2 bar. But mod of real part of z1 z2 bar, it always less than mod of z1 z2, real part less than or equal. Okay. Now therefore it is less than or equals to mod z1 square plus mod z2 square plus 2 into mod of z1 z2 bar, z1 z2 bar. Now it is less than or equals to mod z1 square plus mod z2 square plus 2 into mod of z1 z2 equals to mod of z1 z2, it is equals to mod z1 into mod z2, mod z1 into mod z2. Therefore mod of z1 z2 bar, that equals to mod z1 into mod z2 bar. Now it is less than or equals to mod z1 square plus mod z2 square plus 2 into mod z1, but mod z2 bar equals to mod z2, mod z2. Now it is less than or equals to a square plus b square plus 2ab, mod of z1 plus mod z2 whole square, it is mod of z1 plus z2 whole square less than or equals to mod z1 plus mod z2 whole square. Squares cancel on both sides, therefore mod of z1 plus z2 is less than or equals to mod z1 plus mod z2. Mod of z1 plus z2 always less than or equals to mod z1 plus mod z2. Next, mod, just a minute, modulus and argument form of the complex number. otherwise it is also called polar form. Polar form of the complex number. Mod argument, or here argument is also called amplitude. Mod amplitude or modulus argument form of the complex number, or polar form of the complex number. Polar form of the complex number. Now see it. First, let the complex number z equals to x plus 5y. Now it is also denoted by order pair x comma y. Now take x axis and y axis. Now in the chapter, x axis is called real axis, y axis is called imaginary axis. Now if suppose z equals to x plus I y, that equals to, it is denoted by order pair p x comma y. Now p x comma y denote in the graph sheet. If suppose this distance is x, on y axis y, point p x comma y. Now this plane is called organed plane. In the chapter, x axis and y axis. X axis is called real axis, y axis is imaginary axis, and the plane is called organed plane. Now the point p x comma y. Now the distance between origin to the point p, OP, is called modulus. OP equals to the distance between origin and the point p x comma y, that equals to square root of x minus 0 whole square plus y minus 0 whole square, that equals to square root of x square plus y square. It is nothing but mod z. The distance between origin and the point p x comma y equals to square root of x square plus y square. It is called mod z, modulus of the complex number. If suppose OP inclined an angle theta with x axis in the positive direction, then theta is called argument of z. Now theta is called argument of z. Always it is in the anti-clockwise direction from positive direction of x axis, with positive direction of x axis, anti-clockwise direction. Now always theta lies between minus pi less than theta less than pi, or lies between minus 180 degrees to 180, means up to this 180 degrees, next to in the clockwise direction up to minus pi. Now if suppose draw a perpendicular from P to x axis, PM perpendicular to x axis. Now let OP equals to R. But OP nothing but square root of x square plus y square or mod z, that equals to R units. Now in triangle OPM, here OP equals to R, OM equals to X, PM equals to Y, PM equals to Y. Now, angle POM equals to theta, angle POM equals to theta. Now, in triangle OPM, cos theta equals to adjacent side by hypotenuse x by r, for implies x equals to r cos theta, x equals to r cos theta. Similarly, in same triangle, sin theta equals to opposite side by hypotenuse y by r, for implies y equals to r sin theta, y equals to r sin theta. Now, therefore, z x plus iy equals to, but here the value of x equals to r cos theta plus y equals to r sin theta, I into r sin theta, r take common, that equals to r into cos theta plus I sin theta. Now, where r equals to square root of x square plus y square, r equals to square root of x square y square. Next, what is the tan theta equals to y by x, theta equals to tan inverse y by x. Now, argument equals to theta equals to tan inverse y by x, tan inverse y by x. Now, x plus iy equals to r into cos theta plus I sin theta, where r equals to always square root of x square plus y square, and theta equals to tan inverse y by x, tan inverse y by x. Now, it is also denoted by r into cos theta plus I sin theta can be written as cis theta. Cis theta nothing but cos theta plus I sin theta. If suppose cis alpha equals to cos alpha plus I sin alpha, cos alpha plus I sin alpha, so on. If suppose cis beta means cos beta plus I sin beta, cos beta plus I sin beta. Now, it is called mod argument form or mod amplitude form or polar form Okay. Next, one example. Find argument or amplitude of the complex numbers one is one plus I root 3, second 1 minus I root 3, third or minus 1 plus I root 3, take it, minus 1 minus I root 3, fourth 1 minus I root 3. Now, see it. Solution for first problem 1 plus I root 3, required argument of 1 plus I root 3. Here x equals to, real part equals to 1. Next imaginary part y equals to root 3, y equals to root 3. Now x comma y equals to 1 comma root 3, 1 comma root 3. Now it lies in the first quadrant, because both x and y coordinates are positive, it lies in the first quadrant. Now theta equals to tan inverse y by x, that equals to tan inverse root 3, that equals to pi by 3, 60 degrees, pi by 3. If suppose take x axis, y axis, on x axis at a distance 1 unit, on y axis at a distance root 3 point. Now this angle theta equals to tan inverse root 3 or pi by 3, theta equals to pi by 3, it lies in the first quadrant. Similarly, take the second one, required argument of minus 1 plus I root 3, minus 1 plus I root 3. Now here real part x equals to minus 1, y equals to root 3, y equals to root 3. Now minus 1 comma root 3, x coordinate negative, y coordinate positive, it lies in the second quadrant. Therefore first theta equals to tan inverse y by x, that equals to tan inverse root 3 by minus 1, or tan inverse minus root 3. See it in second quadrant, minus 1 and root 3. Point. It is the point P. Consider minus 1 comma root 3, minus 1 comma root 3, OP. It inclined an angle, this complete angle required, but here minus root 3, in negative side pi by 3. Therefore required theta value. Now theta equals to pi minus pi by 3, that equals to 2 pi by 3. Now that equals to 2 pi by 3, 2 pi by 3, because the point lie in the second quadrant, P. Next third one, required argument of minus 1 minus I root 3. Now here x equals to minus 1, y equals to minus root 3. Both x and y coordinates both are negative, x coordinate negative and also y coordinate is also negative. Now it lies in the third quadrant. Now theta equals to tan inverse y by x, that equals to tan inverse minus root 3 by minus 1. Now x axis, y axis, x coordinate negative minus 1, y coordinate also minus root 3, that equals to point P, minus 1 comma minus root 3, it lie in the third quadrant. Here required this angle, because always theta lies between minus pi and pi, Now equals to, required this value. Now we get this angle equals to tan inverse root 3 pi by 3. Now therefore theta equals to, this angle is theta equals to minus pi plus pi by 3, that equals to minus 2 pi by 3, because always theta lies between minus pi and pi. Next similarly take fourth one, argument of 1 minus I root 3. Here real part x equals to 1 and imaginary part y equals to minus 3. 1 comma minus 3 lie in the fourth quadrant, x axis, y axis. Here 1 minus root 3 point P, 1 comma minus root 3. Required only angle theta, that equals to, here tan theta equals to, at theta equals to tan inverse y by x, that equals to tan inverse minus root 3 by 1, that equals to minus pi by 3. Now theta equals to minus pi by 3, means it depend on quadrant, first quadrant or second or third or fourth quadrant. Next, if Z1 and Z2 are two complex numbers, then the argument of Z1 into Z2 equals to argument of Z1 plus argument of Z2, argument of Z2. Argument of Z1 into Z2 equals to argument of Z1 plus argument of Z2. If suppose, see here, if x plus I by equals to r into cos theta plus I sin theta, here r is modulus, here z equals to or mod z. Now theta equals to argument, of the complex number. Now here theta is argument and r is modulus of the complex number. Now first solution, let z1 equals to some r1 into cos theta 1 plus I sin theta 1, means here r1 is modulus of the complex number z1 and theta 1 is argument, Now also let z2 equals to r2 of cos theta 2 plus I sin theta 2, Now the modulus of the complex number z2 is r2 and theta 2 is its argument, of z2. Now z1 into z2 equals to r1 into cos theta 1 plus I sin theta 1 into r2 cos theta 2 plus I sin theta 2. Now r1 r2 into these two factors multiply together, cos theta 1 into cos theta 2, plus cos theta 1 into I sin theta 2, means I cos theta 1 sin theta 2 plus I sin theta 1 into cos theta 2, I sin theta 1 cos theta 2. Next I sin theta 1 into I sin theta 2 plus I square sin theta 1 sin theta 2. Now that equals to R1 R2 cos theta 1 cos theta 2. Last term I square equals to minus 1 minus sin theta 1 sin theta 2 plus in these two terms I take common sin theta 1 cos theta 2 plus cos theta 1 sin theta 2. Now that equals to R1 R2 cos theta 1 cos theta 2 minus sin theta 1 sin theta 2 cos of theta 1 minus theta 2 plus I into sin theta 1 cos theta 2 plus cos theta 1 sin theta 2 sin theta 1 plus theta 2. Now it is Z1 Z2. Therefore, what is modulus of Z1 Z2? So of Z1 Z2 equals to R1 R2 R1 R2 and argument of Z1 Z2 argument of Z1 Z2 equals to theta 1 plus theta 2 theta 1 plus theta 2, but theta 1 nothing but argument of Z1, theta 2 nothing but argument of Z2, that equals to argument of Z1 plus argument of Z2 argument of Z1 plus argument of Z2. Therefore, argument of Z1 into Z2 equals to argument of Z1 plus argument of Z2. Next, if Z1 and Z2 are two complex numbers, then argument of Z1 by Z2 equals to argument of Z1 minus argument of Z2 minus argument of Z2. Now, let Z1 equals to R1 into cos theta 1 plus I sin theta 1. Here R1 is argument of Z1, theta 1 is R1 equals to mod of Z1 and theta 1 is argument of Z1. Next to Z2 equals to R2 into cos theta 2 plus I sin theta 2. Now, here R2 equals to modulus of Z2 and theta 2 argument of Z2 argument of Z2. Now, Z1 by Z2 equals to R1 by R2 into cos theta 1 plus I sin theta 1 by cos theta 2 plus I sin theta 2. Okay. Z1 by Z2 equals to R1 by R2 cos theta 1 plus I sin theta 1 by cos theta 2 plus I sin theta 2. Now, multiply and divided by conjugate of denominator. Now, cos theta 2 minus I sin theta 2 by cos theta 2 minus I sin theta 2. Now, that equals to R1 by R2 into numerator multiplied, how much we get? Cos theta 1 cos theta 2 minus I into cos theta 1 sin theta 2. Next place I into sin theta 1 cos theta 2 minus I square sin theta 1 sin theta 2 by denominator a plus b into a minus b, a square minus b square, cos square theta 2 minus I square sin square theta 2. But I square equals to minus 1, I square equals to minus 1. Now cos square theta 2 plus sin square theta 2. Now denominator we get 1. That equals to r1 by r2 into cos theta 1 cos theta 2. Here I square equals to minus 1, minus of minus place, sin theta 1 sin theta 2. That equals to cos of theta 1 minus theta 2. In these two terms, I take common, we get sin theta 1 cos theta 2 minus cos theta 1 sin theta 2 by denominator 1. That equals to r1 by r2 cos of theta 1 minus theta 2 plus I into sin theta 1 cos theta 2 minus cos theta 1 sin theta 2. That is nothing but sin of theta 1 minus theta 2. Therefore, here the modulus of the complex number z1 by z2 is r1 by r2 and amplitude equals to theta 1 minus theta 2. Our argument is theta 1 minus theta 2. Therefore, argument of z1 by z2 equals to theta 1 minus theta 2. But theta 1 is argument of z1 minus theta 2 is argument of z2 minus argument of z2 argument of z2. Okay. Similarly, if suppose argument of z1 into z2 into z3 up to so on zn equals to, we get argument of z1 plus argument of z2 plus argument of z3 up to so on plus argument of zn. Here z1, z2, z3 up to so on zn are n complex numbers. Then argument of z1 into z2 into z3 into up to so on zn equals to argument of z1 plus argument of z2 up to so on plus argument of zn. Now, if suppose argument of z1 z2 by z3, it is equals to argument of z1, now numerator z1 z2 plus argument of z2 minus argument of z3 minus argument of z3. For denominator terms we get negative sign. Similarly, if suppose argument of z1 by z2 z3 equals to argument of z1 minus argument of z2 minus argument of z3, so on, like that we get. Okay, thank you very much. In next class we do problems on these models.